Okay, so oh, I'm going to lower the hand here. All right, so now that so last time we marched through our discussion of resistors and resistance, and we're now going to sort of put all that together and start talking about circuits. But this chapter may be the beginning of our slowdown. There's kind of a lot to cover, and a lot of this is stuff that you'll see when you do your simulation. So you're going to play a lot with this in lab, and you're going to have a lot of homework on this chapter. Well, a bit, you know, as much as usual. Um, so circuits are, hold on, I'm a little loopy today. So we're going to be talking about electrical circuits, okay? And electrical circuits form the backbone of every electronic device you use, whether it's your telephone or this pen thing I'm using or the computer you're sitting in front of. But electric circuits are complicated, all right? They have the circuit elements we'll talk about. So they have things like resistors, which you'll see are written like this in a circuit diagram. They have capacitors. We have to learn about these DC circuit elements, right? So as far as circuit complexity goes, we have DC, then we have AC, and then we have solid state, analog, and then we have solid state digital. Basically, you use all of these components, you get a lot of your power from these edge. These deal with power delivery, and these deal more with devices, like to do things to manipulate and control currents. And that's important because you can use these solid state devices eventually to create logic gates, which allow you to do things in terms of ones and zeros, which allow for you to do computation. So we're only going to stick to AC and DC in the class, which focuses more on power delivery and load dissipation. But a lot of the concepts that apply here will actually all of them will transfer directly to your learning of more advanced circuits. And so here you get things like resistors and capacitors with batteries. Here you have inductors. You deal with magnetic fields in addition to those other two elements, and variable sources. Then you get to things like transistors and operational amplifiers, and diodes in these solid state analog devices. And then you can create from those analog devices digital devices, all right, or devices that can handle digital input and output. So you make switches basically. So circuits is fundamental and probably the most obviously applicable chapter that we will cover in this class. That doesn't mean it's the most applicable. We're gonna, as you're going to see, we're going to keep adding more to this. But this chapter is very, very application based. But that being said, we have a lot of terms and a lot of words to go over. Okay, so look at all that word barf. How's that for anger? So I'm gonna talk over this slide. I'll let you read it. But I want to point out some things we're seeing for the first time here. We have a battery, which we're not seeing for the first time, but we're going to introduce but we talked about resistors and resistance last class, and in a circuit diagram, resistances are labeled with this sort of triangle sawtooth wave here, all right, and labeled R. Now, you'll notice last time on Physics 2, the great online experiment, we related voltage. Oh, that's a crappy choice in color. We related voltage, right, to current and resistance. But now, if you look at this, we have a resistance, right? We have a current. And now it's fair to ask, what the hell is this? It looks like a voltage, but now it's got this squiggly E. And if you're drawing it, you can just draw it like, I just call it squiggle. It always looks like that. I've been trying to draw it right for years. So one of those two things, that's how you'll see it. You drawing it. So we want to talk about this quantity, all right, which is called the electromotive force. So if we have a device that produces a steady flow of charge, I want you to notice some of the wording here, right? So to produce a steady flow of charge, you need a charge pump, a device that, by doing work on the charge carriers, maintains a potential difference between a pair of terminals. Ooh, I don't like this part of it because, and I'll explain why in a minute. We call such a device an EMF device, and the device is said to provide an EMF, which means it does work on charge carriers. I like this sentence. This part, not so much, because for DC circuits, and in an ideal circuit, you're going to notice that this squiggle is just the voltage. In a non-ideal circuit, right, which we will talk about, you'll have the EMF, which will be the effective voltage, right, or this effective EMF, and you'll have this delta V, all right, and then you'll have that these will be equal in an ideal circuit. In a non-ideal circuit with a non-ideal source, epsilon will always be a little less than the voltage, okay? And there will be times, you know, this is sort of a sidebar, so I'll put it in a box over here. We will find situations where the EMF is not equal to 0, but the voltage is, or the change in voltage rather. Delta V equals 0. I'm going to put that as delta V. Okay? So we will find cases where that happens. So if you think they're exactly the same and you can just sort of set it and forget it, you are incorrect. Don't do that. But looking at it, looking through it, you can read the rest of that. Some of this is just rehashing stuff we've talked about the battery. And you'll notice that the EMF, we have this arrow from the lower potential to the higher potential, and we have the current still flows from higher potential to lower potential, all right? And again, this is assuming currents are positive charge carriers. You can tell that because it looks like it models that the current will push positive charges around the circuit, okay? So current, or the EMF, if we're defining it, you're going to notice has nothing to do with voltage. And I would remind you that the change in potential, the potential difference, is defined in terms of the electric field, whereas the EMF is defined in terms of work done by charge. All right? So you'll notice this slide talks about the ideal EMF, right? And you can see here that they have in the ideal EMF, the potential difference is equal to the EMF. So look at what's underlined. So, and in a real EMF, there's internal resistance. What that means is that in this battery, there's a small resistance, and the ideal battery would be given here. That would be your delta V. And then here between the two terminals and the resistance, that's your EMF. Okay? And so if there's no current going through the device, then you can say that delta V is equal to, I don't know if this is an epsilon. I usually just call it squiggle, to be honest. That's what we're going to call it. I know it seems ridiculous, but we're just, because we already have epsilon in the course, and I don't think that's an epsilon at all. I'm pretty sure it's just a squiggle. So we're going to call it squiggle. So squiggle will be equal to delta V only if there's no current in this system. Okay? I think we'll see some cleaner pictures of a real EMF device as we go along. Let me get this. Yeah. Okay. So, oh, okay. So we won't see one quite yet. So I'll draw one. So I'm going to try and make a nicer drawing. So we have our battery here. All right, with our positive terminal and our other terminal. So inside the battery, to just illustrate it, I'm going to try and draw it really. I drew it a little terribly before, but boo. Okay. Oh, hold on. There we go. And then we'll get the pencil and we'll try 1, 2, 3, and then out. So it looks a bit like that. That's still not a great drawing, but I think it's a little more clear than my scribble here, where you can see your ideal battery, your ideal source, and we'll write. Let's draw this just a little carefully. So here, that's delta V, and between these two terminals, that's squiggle. Does everyone see the difference? You know, what the EMF in the battery here. What I'm saying between. Are there any questions on what I'm saying here about EMF and potential difference? Because they're gonna seem exactly the same for most of this chapter, but they're really not. Okay, so I'll give you a minute to sort of think about it. Well, remember the difference. The real difference is that potential difference between 2 points is defined in terms of the electric field, right? So this is a field argument. And squiggle, or the EMF, is defined in terms of the work done on charges. So in terms of DC circuits, these look the same. So they're going to look the same now. So the battery is just one EMF device. Is there any other example of an EMF device? Sure. None that'll really make sense now, but like you can have a function generator that's an EMF device. You can have a magnet act as an EMF device. You can have other EMF devices. And the units to be more confusing, the units for EMF are volts. I mean, they look the same, but they're not quite the same, and they are defined differently. You can't define the potential. I don't know that it makes, let me see, because we define potential, right, as, well, you'll notice we define potential difference in terms of potential energy that we associate with an electric field. Here we're defining the EMF with work, right? And there are ways to relate them through the work energy theorem. I'm not saying there aren't. But like I said, we are going to find cases where these two quantities, when things become more complicated, there will be clearer differences between them than there are now. But for right now, our EMF device is our battery provided by our battery, our potential difference. But it will be possible to have EMFs without a potential difference, which we'll see later in the semester. All right. So we can redefine Ohm's law in terms of remember again, squiggle is equal to d work dq. Okay, so considering energy, we can define the power. Oh, Jesus. We can define the power dissipated in a circuit. If you recall from our last chapter, it's I squared R. Okay? So what that tells us is that, and if you recall, power is equal to d work dt, right? So if we look at that, you know, we make some assumptions here. We assume that wires have to have negligible resistance, and then so that if they have no resistance, no thermal energy will really appear in them. And we also want to recall that I is equal to dq dt, right? So if we look here, so if we look here at this part, we can say that the work is equal to Q, or not Q. That is a mistake. It's equal to squiggle dq, right? And then from there, we can see that dq from here is equal to di. No, I'm sorry. I'm writing ridiculousness here. We can say here that I want to delete this too. From the definition of current, right, we can say that dq equals I dt. All right, now sort of looking at this here, we can see that using our transitive properties here, that that our power, right, or our work, sorry, d work will equal squiggle dq, which will also equal squiggle I dt, right? And now, if we look here, if we look at this at our equation here, we have a work equation, and so from conservation of energy, the work done by the ideal battery, right, which is this, must be equal to the thermal energy that appears in the resistor. So now we get back to the power. So we have power dissipated thermally, work done by the resistor. Okay, and so we have we can say that basically the work done here, dW, dW, right? If power is equal to dW dt, I squared R, this implies that dW also equals I R squared dt. All right, and this equation here is just equating what we have here and what we have here. All right, so the important part of understanding understanding the circled equation is to understand that we are approaching this from conservation of energy. All right, we have our circuit, and it's a single loop circuit. So we start off knowing a few things, right? We have our definition of squiggle, or the electromotive force here, of our EMF. We have our definition of power from physics 1, and we know that the thermal work, the work done by thermal energy, the power dissipated to heat, is I squared R. All right, so we have power equals d omega, d work dt. Now, what we also have that the work done by pushing the charges from the electromotive force is the electromotive force times dq equals I dt. And so what we get here is we have an expression for the work done by the electromotive force, right? Which is equal to squiggle times I times dt. And we also have that the power dissipated, the work done, is equal to I R squared, that's the thermal dissipation, times dt. And then we set those two things equal to each other. And they're equal to each other because energy is conserved, right? The work done on the charges has to lead to the dissipation of thermal energy. There's no other source of energy, and that's it. All right? And so from here, from the circle equation, which is squiggle I dt equals I squared R dt. You just cancel everything that repeats itself, so there's an I dt, and you get squiggle is equal to I times R, which, solving very simply, gives you that I is equal to squiggle over R, or the EMF over R. Okay? So, questions there? There was a lot of fun derivation stuff in there. All right. Good. I don't know why my voice is so scratchy. I was talking just fine earlier. Okay, so this is one way to look at this, and it's rather difficult. We're now going to look at this in a little bit. We're going to be very clever, I guess one could say, when we go to the potential method. All right. So the potential method is going to give us some machinery to analyze circuits. All right. And we're looking at the same figure. It's the same circuit, right? I'm going to get this here. We have the same circuit with our EMF battery, our ideal EMF battery, if you will, and our current. But you'll notice that we go around the circuit. We're going to go from A, go around the circuit, and go to A, and we're actually going to analyze each of the circuit elements. Okay? So now let's talk about how we do this. Basically, we pick you make a loop in the circuit. The zigzag is, yes, I call it squiggle, but this thing is the EMF that the pointer's over. All right, so let's start at A, and let me show you how to construct a loop. All right, so when you look here, zigzag is the, wait, this is the EMF, this is the resistor, right, and the current goes around. Okay, so I'm pointing right to the EMF right now. I'm moving the cursor. Okay, all right. So basically, we pick a point and start anywhere on a circuit. And circuits can get pretty complicated. Right now, we've only looked at single loop circuits, so it's kind of trivial. But you pick a point, and you assume it has any voltage. So you call it V at point A. All right, and it's just a number. It's whatever it is. So now we go from A, right? And you ask yourself, am I going up a hill or down a hill? Am I going from lower potential to higher potential, or higher potential to lower potential? Okay? And as I go around with my loop, I'm here at lower potential, getting to higher potential. So that's going to be a positive contribution. So when I do that, I add my EMF, my squiggle. But now as I continue to go around the circuit, okay, as I continue to go around the circuit, you'll notice that this resistor, this part of the resistor is at higher potential and this part's at lower potential. Now it's really clear to see this here because literally you're connected to higher potential here and you're connected to lower potential at this end of the circuit. All right? So when you go down from higher potential to lower potential, you're going down the hill essentially, and you have minus. So we're going to call this minus, but we're going to call this minus IR. And now when we continue to go around the circuit, we're going to get all the way around to A, which is back where we started, and nothing's happened in the circuit to change its potential. So we can say that once we add all those terms together, we should get VA back. Now, the algebra here is very interesting. You have VA on both sides, and that makes sense. And what we can see is that the potential around any closed loop, my computer wanted to have an issue there, will be equal to 0. And that's pretty cool, because that's going to be a very powerful technique that we're going to use to be able to analyze very complex circuits. Now, in more complex circuits, when you have many loops going and it's not clear where the resistor really tracks back to, you're going to assume the current goes a direction, right? And if you're going, as you go through, if you're going with the current, as you make your loop go through the circuit, if you're going with the current, then this term will be negative, right? That's where the negative sign will come from. And say you went around the opposite way. You went around the circuit this way. And if you look, I'm going opposite the way of the current I assumed, then you will have this term actually be positive, right? But in that world, right, this term is positive because we're going from lower to higher potential. And then we're going from here, we'd be going from higher potential to lower potential. So the signs would flip, and you'd essentially get the same thing. You're going to want to be careful with this. I think one of the more uncomfortable things to do is to just guess which way the current is going. I can already imagine and I can imagine it because I remember doing it. A lot of you getting frustrated trying to figure out which way the current goes first and being uncomfortable with that. Just guess. If you get a minus sign, it means you picked the wrong way, right? That's all a minus sign means, is whatever assumption you made about the currents, you keep track of the first one you pick and then the consequent from all that. And if you get a negative number, you're very likely you just pick the wrong direction. It's no big deal. You just go, oh, I picked the wrong direction, and you flip it back, and then the other stuff should come forward. But you gotta keep that in mind. You're gonna have to guess those currents and see if you're right. That's all you can do. Okay. So, all right. So, does this make sense how we got this equation and these equations? And then you'll notice with the here we got it back. Now I want you to notice that it's almost like a trick, right? Because this was much cleaner to do than the energy method, right? But the energy method the energy method's important because even though it's a little more convoluted, it keeps that connection to our physical models. And I sort of want to pull back that even though we're getting very specific and applicative here, that physics is about sort of setting up a paradigm or a model, a theory like the conservation of energy, and showing that everything follows from it. And that's sort of what we're doing here. And it may not be clear, but energy, much like in Physics 1 where we start with forces and then move to energy, we're sort of in the process of doing that here, of finding that while we will talk about forces quite a bit because they're intuitive, we'll almost always end up at energy. All right? And what you can see here is that even using potentials, our loop law, another way of looking at this is that our loop law is just another expression of the conservation of energy. And that's going to be important as we develop more sophisticated models. Its basis is off of not necessarily, that's mechanical energy specifically, but basically, yeah. Yeah, its basis is off of the internal energy is conserved. And we saw that in the last slide, right? If we go back here, we can see that basically by applying conservation of energy, we get the result from our loop law. And we can see here that our loop law is sort of an equivalent statement of the conservation of energy. Okay? All right. So okay. So we will get to that internal resistance in a little bit, but we have some techniques we're going to want to talk about. Okay? So calculating current in single loop circuits, and again, when we get to multi-loop circuits, these will be important. The loop rule, or the Kirchhoff's loop rule, is the most important rule, all right? And that is that the algebraic sum of the changes in potentials encountered in a complete traversal of any loop of a circuit must be 0. So the important words here that really make this powerful are the seemingly little ones. That's any and must. All right, so keep those in mind. So the resistance rule. For a move through a resistance in the direction of the current, the change in the potential is negative IR. In the opposite direction, it's plus IR. So we saw that going back. That second rule is just telling you what I told you here, right? If you're going through the circuit, we'll get the pointer. If we're going through the circuit, right? If in our loop, we're at the resistor. As I go through my loop, I'm going with the current. That's a negative contribution. If I'm going against the current, that's a positive contribution. And you'll notice that's exactly what it says here, right? If we move through a resistance in the direction of the current, the change in potential is minus IR. In the opposite direction, it's plus IR, right? And then let's see what our last one is. For a move through an ideal EMF, in the direction of the EMF, the change in potential is positive, and in the opposite direction, it's negative. We'll go back and look at that one too. So again, when I'm going through here, I'm in the direction of the EMF. That's a positive change. If I were to come the opposite way and go against the direction of the EMF, that would be a negative contribution for the EMF, for squiggle. All right, which is exactly what it says here. Okay? All right. So, internal resistances and what they mean for us. So, internal resistance makes lets us look at a more realistic system. All EMF devices have some sort of internal resistance. We're not really going to talk about superconductors, but that's okay. And we have a loop here with a non-ideal EMF, right, and a load resistor here. Okay? Notice the current goes, again, from the positive terminal to the negative terminal. All right. So we have in our idealized battery here, we have our EMF, and we basically add this other resistor. Okay? So when we go through the loop, let's apply the loop rule very simply. And they do it down there, but we'll do it up here. Right? So start at terminal A, and we go up the hill, right? So that's going to be E, or a squiggle, right? And then minus I little r. And then as we go around, because we're going with the current, again, minus I big R, and that's going to equal 0. Let's look at it here. So at the potential, since we can pick any value and it'll go to 0, it's easiest just to pick 0, right? We get to the EMF device, we go up the hill, right? That's this part, and that's this contribution. And then we get to the internal resistor, and you'll notice the resistors, as we get to it, right? We get to it very quickly. It's in the direction of the current, so it will go down, right? And then we'll have this R here. This next R will go around the circuit. We hit the next resistor. We're going in the direction of the current, and we hit R. Okay? So when we hit R, we're going again in the direction of the current. That'll be a minus term because we're going down the hill. And then we get back to A. So this just represents one loop through the circuit, through each part of it, okay? And you'll notice that with this idealized, with this ideal battery, I is just going to equal to the EMF over R resistor plus the big resistor. And in fact, you can almost sort of think of these as, in some ways, as two resistors in series, right? And we're going to extend series and parallel to resistors today in this class, because we've already talked about that with capacitors. And it's going to make a lot more sense because we'll be able to talk about it in terms of current. All right. Oh. No, not really. So with the Taylor expansion, right? You have a Taylor expansion is breaking a polynomial or a function into a polynomial, right? So there's a x to the 0 plus a1 x to the 1 plus a2 x squared. That's usually how Taylor series work, right? So we're not really expanding anything. I mean, it kind of looks like a geometric series, I guess, but in series, when I talk about series, it's more like it's how the wiring is constructed. It's not really it's not a calculus thing. So this series, it's like we did capacitors in series. The Taylor expansion pertains to functions, and the Taylor expansion is the most important thing you learn in calculus as far as applying math, or in physics. Like when you start doing more advanced stuff, engineering and physics, you will need those Taylor expansions till the end of time. But right now, no, we're not really approximating anything. We're just saying that, what I mean by series is that we can think of this as two resistors with the same current going through them, all right, connected to this ideal EMF. Yes. So remember, that again comes from, in fact, I'll go through the loop again. Now remember, it all goes to following those rules from the previous slide. So our rules for calculating current in single loops here is given here, our criteria. And I'll go through it as we go through the loop again. So let's start at point A. So I'm going to try and do this all with the mouse. I don't think it's going to work well. So we start at point A, right? So we can just call that 0. Let's look at it over here. So now using our criteria, we get to a battery. So we can always check the battery, but we're assuming the current goes around in this clockwise manner, and we're choosing a loop path that goes the same direction of the current. That's sort of the first thing to notice. Okay. Now, when we start at point A, we reach this EMF, right? So we reach an EMF. Now we have to ask the question. We can see from the EMF, from the design, that we're going from the negative terminal to the positive terminal, right? And is this arrow going from negative to positive in the same direction or the opposite direction of the current? And that tells us whether it's plus or minus. So here, I know you asked about the IRs, Mustafa, but this answers the whole question. So we see here that they're going the same direction, so we get epsilon, or squiggle, right? And that's positive because we're going from plus to minus. Now we're sort of done with that here, right? At this point, we reach the resistor, little r. So now at this point, we have to ask, as we traverse this resistor, are we going with the current or against the current? We're going with it. So our rule tells us that we have a minus sign. Okay? And then we do the same thing, and now we're at point B. There's nothing really at this point B. There's just some potential difference or voltage. So we go through, and you'll notice that here we went up the hill, and then at that resistor we went down a little bit too. All right, and then when we get to VB, we're going to get to this, as we're at VB, the voltage doesn't change until we hit the resistor. All right, and now we have to ask ourselves again, are we going with, when we're here, are we going, as we traverse the loop, are we going with the current or against the current? So as you can see, we're going the same direction as the current, right? With the current. So if we're going with the current, again, that means the contribution will be negative, be minus I times big R, right? And you'll notice here we drop down to our voltage at A, and we get right back to our point A at the battery, right? So we know that this then, since we've made one loop, will equal 0. Okay? So that's where the minus signs come from. The green line, no, it's not the potential energy, it's the potential difference. We got to be careful because we're going to start calling potential difference potential. Notice that, look at the units. If it were potential energy, it would be joules. The units here are volts, so that's potential difference. So if we didn't have a resistor on the right, then this term would just be crossed out. All right. The more interesting question to ask probably, no, because as long as you close the circuit, right? If you remove the resistor, if you just take it out and it's a broken circuit, then no current can flow. But if you close the circuit, there's no reason why current wouldn't flow. So it's not really a dumb question actually, because if you remember, we have to go back a way. But remember that potential is just a different type of quantity, and that U, potential energy, is equal to Q times delta V, the potential difference. So what that means is that the potential, volts, if you will, are the energy specifically stored per unit charge. Okay, so that's joules per coulomb. Yeah. Okay, and they're both scalar-ish quantity or scalar quantities. EMF is a scalar-ish quantity because it certainly has an implied direction. But we definitely don't treat these like vector equations at all. Joules is to kinetic as no. The units for potential energy and kinetic energy and all energy is joules. Potential is something different. It's joules per charge. So this is joules, this is coulombs, and this is volts. I don't think the analogy works, that particular one. No, because again, we're dealing with the literal building blocks. So making an analogy of those building blocks will just get confusing. I wouldn't do it. Anna, what do you want me to explain specifically? You want the process of which? Did you want me to go around the circuit one more time? Okay, I'll do that as soon as I'm. We'll do that before we move on. I just want to make sure I'm all right with Lewis here, with the analogy versus the thing, because you have to be specific, especially when you're dealing with volts, joules, and all that stuff. Well, no, watts is the power. So what you want to look at is you can use the conservation of energy to develop our expressions for V and E, right? Delta V. A lot of this stuff that we do is developed from conservation of energy or the work energy theorem. And we can use conservation of energy to come up with an equivalent result to the loop law, right? E being the electric field, yeah. So, but when we developed our definitions for delta V, including this one here, we used energy conservation. And what I'm just trying to show you, at least how these are related, is that the loop law is a result or an application of energy conservation. It gives you the same results. All right, so I'd say that the loop law, applying the loop law to a circuit is equivalent to applying energy conservation, but you know, that's as far as I would go. I wouldn't start assigning roles to other things. I think the trouble you're having is probably more common than you think. Looking at these things, but we should, I mean, I guess what I can say is that you want to keep, you know, if you're bookkeeping these yes, so this is potential energy, this is volts, this is charge, right? And then you have the definition of V here, where this here, U is potential energy, and then these are just the units. Okay? So I want to do this, I want to go around when we're looking at that, go around the circuit once again to look at the process. So yes, that's the way to look at it, yeah. And there's no analogies there. All right, so I want to go around, I'm going to go around the circuit one more time because this skill is incredibly important for understanding how to do these multi-loop circuits. So let's start at A, all right? And we're just going to apply, we're going to ask the questions. Like I'll go back and forth actually as we do it, and I'm going to use the written down equation on the slide. This equation here is the one we'll be using going forward, and it's just written down here. So I'm going to go back and forth, and I'm hoping this might help. So we're going to start at A, all right? And we're going to get here to a battery, an EMF device. We can see this is the negative terminal, this is the positive terminal. So we know that the EMF points in the direction of the arrow, and we've assumed that the current is going clockwise. So now we have to ask ourselves some questions, all right? One, why are we doing this? We're doing this loop rule because we know the algebraic sum must always be 0, all right? So that's why we chose a direction for the current, and that's why we started at A. Once we get to this EMF, we have to ask ourselves, is the direction of the EMF equal to the current? All right, we can see that back here. I'll answer your question, Louis, after I go through the loop. So we go here. So we look for, as we move through the loop, if the or we're at it. This is for resistance, EMF. So if we move through an ideal EMF in the direction of the EMF, the change is positive. If it's the opposite, it's negative. So as we look through the circuit, we have to ask ourselves, are we in the same direction as the current? That's always the question you have to ask. So here, the current is pointing up, and the EMF is pointing up. So that means we have a positive contribution. Okay? And now we get to, so now we're done with that. We have squiggle written down, and now we get to the resistor that's internal to the battery. So now we have to ask ourselves, are we, as we go through this resistance, are we going with the current or against the current? Meaning, am I moving through this resistor in the same direction as the current or the opposite direction? As you can see, I'm moving through the loop. Hold on. I'm moving through the loop in this direction, right? And so I'm going with the current. So that means I look at the resistance rule and it tells me that I have a negative quantity. And so I have minus IR. All right? And then, does that make sense so far? You've going through the loop? Okay, good. So when we go, as we continue to go through the loop now, we're not hitting anything, right? We're just at I, we're going along happily. And now we get to another resistor. And once you get to the resistor, the question you ask yourself is, am I going with the current or against the current? I'm going with the current, so that's going to be a minus times IR. So again, you'll notice that that's the voltage across the resistor. The voltage I little r is the voltage across the internal resistance. And then when we get to R, IR is also the voltage across the big resistance. So I want you to notice that our asking our questions as we get to each device dictates what signs we have here. All right, and you'll notice that each of these quantities has the units of volts. And again, we're doing this because if we go around one loop, that ensures that everything's equal to 0. Okay? And you have a pictorial, figure B here is a pictorial representation of us going from that point A in the battery. You notice we go up from the EMF, we go down from the internal resistance, and we go back down to the same value as we get, or the same potentials we get back to the same point. All right? So, all right, let me see. So if the potential difference integral of the E field, so if what's equal to 0 is right, any other value is wrong. I'm not sure I understand your question, Louis. You can put on your microphone if you want, if you have it on there. It might be easier verbally.
So I see that on one of the slides that you put that the, hold on, let me see if I can find it. I think I saw like the electric potential was equal to the integral of E times ds, and if E is the electric field, would that be related to K times Q over D?
K times Q over D. Well, yeah, but K times Q over D is for a point charge, right? So it's
right.
what's really important. What you're looking at is the charge distributions. So when we looked at electric fields and potential differences, we looked at very set charge distributions. When we talk about electric circuits, we're talking about lots of charges moving, and we're talking about like a current of many charges, sort of.
Okay. So set charge distributions are more like are static, while the other is dynamic.
Well,
it's moving,
well,
correct?
it's I would say it's sort of dynamic because we're certainly looking at charge. So the electrostatics will probably cause the charge distribution in here, right? Mm-hmm. So that's a static charge distribution. But then as it charges or discharges, charges will move. So you're more looking at so instead of looking at this stuff like having to solve for a new potential difference each time, you sort of we're sort of developing rules that let us look at this system very easily instead of being very complicated, and seeing that those quantities relate in general. So for instance, if you're solving for when you solve for the electric field, you look for the field due to a charge distribution, right? Here you assume point charges are moving, so you assume you have on the battery, right, positive charges up here, negative charges down here. So you just make those field lines follow the current, right? And that there's a conducting path. So that electric field actually follows the conducting path and moves through here. That's what the last chapter was really about. Chapter 26 handles this stuff in the nitty-gritty, and it sort of helps us move from, because I don't want to say dynamic really, but what I would say is it sort of helps us move from single charges and charge distributions to sort of bulk problems, and I call this more of a bulk problem.
So right. Okay, so when I saw the point charges and I saw pictures of it, it's kind of like the topography of mountain regions, right? Would that here be just those say mountain ranges moving along the circuit?
Yeah, but that would be a super complicated way of looking at it.
Okay, well, I don't know. It makes sense to me that way.
All right, if it makes sense to you, I would say you're not wrong as far as visualizing it, but as far as solving, like, we're not going to find electric, we're going to be very sparing with the electric field when we talk about circuits, for instance. But it is, and that's mainly because it changes direction due to the conduction path. So there's just kind of more going on. But yeah, you could think of those point charges, those distributions moving along a circuit. I think that, yeah. Okay. We can go over more of it later during office hours or something, if you'd like. But it is 6:58, so let's take a break till around 7:10 or so. And I'm glad we're slowing down a little bit with this chapter, because I was really hoping we could straddle this chapter between spring break. I didn't want to get it all done tonight. So, okay, so let's come back at let's come back at 7:12, 7:15-ish. We'll get started, and then and I think I have you guys till, let me see, I've been doing stuff on the CUNY first. No, I should be in CUNY first. Actually, let's be sure. Yeah, 7:55. Okay. All right. All right. I gotta plan some dinner and things, so I'll be back in a couple minutes. My Skype is my work email, and you just pick the fish avatar, because there's a few accounts associated with it. Yeah, it's All right, I'm back, but we'll still 2 minutes. Let me read what's going on. Oh, I gotta turn on the light. Yeah, Skype is easier for me because I can just leave it on and people chat on it, and I can get questions, and I can at least respond if you do the questions there. I can respond there without it taking up a bunch of email space, and I just always have the alert. So it's only for students, so I know that everything is just you guys. So that's probably the better way to get in touch with me if you have a message about anything. Zoom is great for everyone to video conference all the time, but that's not really usually what we do in office hour. Yeah, 5. It's annoying to check sometimes. So nothing's coming up. JTOLAND@lagcc.key. I'm there. Let me see if you added, because I have like 10 people on here. Yeah, a dory pick comes up, the fish, and I'm on right now. So I have to get a thing that says you know that you want to be added. Oh, PB. Okay, let me see. Oh, I see what you mean. All right. There, I sent you the thing. It has the little thing that waves. Good. All right, no problem. Okay. All right. Mm-hmm. Yeah, so session 2 classes are going to be distance, and we'll see how many people sign up. I'm going to be running a summer physics 1, and they're even talking about fall being distance. But well, they're talking about fall being hybrid. But honestly, there's no point to meeting. You either should meet or not meet at all, right? So in the fall, if they want us to only meet somewhat, that's actually going to do virtually nothing. So, you know, we'll see how long this whole thing goes on. I really thought we'd be around the bend by September, but I don't know. They're still arguing. Yeah, no, it really does. It really does. It's not my favorite thing, that's for sure. That is for sure. Well, we do. It's in the dumper. So virtually 6 million jobs, I believe, have been lost. So yeah, I think it'll probably be up to 10 to 20 million by the time September rolls around. 2020 is basically, yeah, 2020 is canceled. That's a good way of putting it. All right, let me just check and see. Okay. Yeah. Nope, 2021, 2022. I guess let's bring them on. I don't know. The way I look at it is my cost of living is decreasing this year too. So going to the grocery store, I have seen the light as far as saving money for food. All right, but let's get back to it. Okay, so we've talked about these. Oh, that's what I didn't get water. I was so busy prepping dinner, I didn't get water. So we've talked about making our loop for a single loop circuit with one resistor. But now we're going to talk about having multiple resistors in series. So you'll notice we had a system where we looked at this with capacitors. So that's why we spent that time defining series and parallel in the capacitance chapter, and which may feel like a long time ago, but was very recently. And what we're going to see is, you'll notice we have this battery or this EMF device, and now we have R1, R2, and R3. And much like we had with capacitors, we're going to find that we can make equivalent circuits from 3 resistors to an equivalent circuit. But we're going to ask ourselves how to do that. So we can actually do that by stepping through the loop law. All right? So we'll start at point A. I'll highlight it with a pencil. We'll go around. We've already established, so usually the first way to go is clockwise, and you'll notice we've picked a direction for the current, right, based on our battery. So we get to this potential, or this EMF device, and our EMF device is going the same way as our current. Our current should be going this way if you follow the arrows for the current. And so in our equation, that will be our squiggle, right? So that's okay. So now we go past the EMF, it's positive. We get to our first resistor, and we're going with the current, so that'll be minus I1 R1. Okay. Now we go through here. We continue around the circuit. We get to resistance 2. We ask the question again, are we going with the current or against the current? You'll notice we are going with the current, right? And so that will make this I2 R2. Okay. And now we get here to R3. And you notice it's the same thing. We ask the same question. We get the same answer. We get I3 R3. Equals 0. Okay? That's what the loop law says. But now we can do some analysis. So if you recall, right, if something is in series, I want to just delete some of the craziness here. Right? If this circuit is in series, then the current that's established from all the resistances and the EMF is the same. All right? So we in fact don't need I1, I2, and I3. We can simply rewrite this equation as IR1. This one will be IR2. This will be IR3. Now, I like to do that explicitly because you really should look at the circuit, make that decision, and then take off the subscripts. Because when you do that, you allow yourself to sort of develop a way of analyzing circuits in which you can ask yourself, are the currents the same or aren't they the same? Which is what you should be asking when you look at something in series, right? So here the current has a place to go but around the single loop, and it's all going to be the same. And you'll notice that if you look here, you have this equation, and you will notice that if you look at a equivalent circuit, right, in which all the resistors are replaced with one resistance, which is this one here, R equal, oh darn it. Right, R equiv, you'll notice that on looking at this one, you would get that I through that circuit is equal to E over R equiv. Okay? And so what we can see here is that the equivalent R is equal to R1 plus R2 plus R3. And in fact, if you have N resistors in series, you just simply add them up. And in a way, this makes sense, right? If we think of resistance as something that impedes current, the thicker you make the wall, the harder it is, the more it impedes the current, right? So that's how resistance should add. You'll notice that this is not the same for capacitance, though. But again, we're using the same sort of principle to get the equivalent formulas. But the equivalent formulas, well, they're a little different. So for resistance in series, it's R1 plus R2 plus R3. All right? So here we have our equivalent, R1 plus R2 plus R3 with our general equation. Okay. So we have a checkpoint here with the same thing. So when we look here, when a potential difference is applied across resistances connected in series, the resistances have identical currents. We already established that when we talked about capacitors, right? The same charge would be on each capacitor, therefore the same charge per unit time or current would flow through the, well, I'm doing that basically right now. So if you look here, you have the same current, right? On each part. So the sum of the potential differences across the resistance is equal to the sum of the potentials, or to the potential across the EMF. And let's go back and take a look. We can sort of see that, right? The potential, if we look at this, let's do one step in between here that will explain these steps a little further. So if we look at this, we can see that we have the EMF on one side, right? And we have the potential, that's the potential drop across resistance 1, plus the potential drop across resistance 2, plus the potential drop across resistance 3. And I say that because in either way you want to look at this, it's either delta V equals IR or squiggle equals IR. Either way you look at it, that's what you're getting, okay? So that's what we're able to say. And that's kind of the last part of the slide. And that's well, I'll go over the equivalence part again too. So because of that, right, and we were looking at that, this is on the next slide, but because of this, we can factor out the I, and we're left with this form. Now, an equivalent resistance, we're saying, is that you can make these into one in series, and we're just trying to figure out the formula for it. So if you were to do that, you'd look at this circuit, right, and then you'd look at this and say, so for this circuit, it's equals I R equiv. Okay? And solving for the current here, you get that the current, because the currents have to be the same in the circuit, you get that this whole expression is equal to, hold on, So this whole expression is equal to, period notwithstanding, our electromotive force over R equiv. And then all we do is we equate the denominators, right? So these two things have to be equal, and that's what we get here. It's just writing that statement. All right, that connects the equivalent resistances. Does that make sense? The part for this whole slide to be good with is this equation. All right, and we get that. First we do our loop law, right? And we get this equation here. Hold on. We get this equation that the cursor is pointing to. All right, and again, we always look at the EMF, the potential difference, the potential difference, the potential difference. And what we saw here is that the EMF, right, is equal to the sum of the potential difference drops across the resistors. This is just a consequence of the loop law, right? It seems like it's something new, but it's really not. It's just a direct consequence of it. Now, when you look at these a circuit here, you can solve for the current in this from the loop law, and you get that it's the EMF over the sum of the resistances. Now, no. It's equal to 0 here. I'm pointing to it right here. Once you set it up equal to 0, then we're not changing the rules or doing anything different. We're just doing algebra now. And algebra gives us the consequence. Okay? So after that, then we get this top equation. All right? And that's to make that point. That the EMF is equal to the sum of the voltage drops across all of these resistors. All right, and when we do that, we can look at the equation for each for the system, and then the equivalent system, and then equating those denominators, we get our expression for our equivalent resistance in series. Okay, and then that gives us our general equation. So going back to this slide. Resistance connected in series can be replaced with an equivalent resistance, R equiv, that has the same current and same total potential difference as the actual resistances. All right. So I want to do a checkpoint to see how we're doing here. I like this one. So in the figure here, whatever A, so it's this one, right? R1 is bigger than R2 is bigger than R3. So we want to rank the three resistances according to the current through them and the potential difference across them, with the greatest first. Okay, so take some time and try and answer that one. Think about, and when you're doing it, think about what we said about what it means to be, look at the figure here, and think about its series. This is what we're looking at, it's this figure, right? So think about the values of the currents through all the resistances, and then those individual drops that we just looked at. Okay? The task is in checkpoint 2, right? You have R1 is greater than R2 is greater than R3. So you want to rank the current. So look at that here. That's basically saying R1 is bigger than R2, it's bigger than R3. All right? And then you want to look at A. Part A is what is the current? You want to rank the currents on each of these resistances, and then you want to rank the potential difference. So basically what you're looking for is you want to rank the so for part A, it's you want to look at I1, I2. Hold on, I1, I2, and I3, and figure out the relation between those three. And for part B, you want to do the same thing, but for voltages. You want to find the relation between V1, V2, and V3. And you already have, this is the relation for R, right? So basically you want to come up with something similar, but for your I1s, I2s, and your I's and your V's. Okay. Hmm. So think about what we said about the resistor, or about the series circuit, all right? And read the two things on top if you have to. Those two stars should help. Ah, that is a possible answer. Good. Right, the answer for A is that. Right? And then it's, well, you got to look, right? V is equal to IR. So if R1 is the biggest, I think we would expect that V1 would be greater than V2, would be greater than V3. Yeah. All right. So see if you have any questions about that. Take a look at it and make sure that makes sense. Well, the I's are equal because of the definition of series, right? If a circuit is in series, the definition of a series circuit is that the current is established and goes through the whole loop, or the whole circuit, right? And in fact, that's kind of true of every circuit. We'll see that in multi-loop circuits, the current will have places to break off and branch off. All right. So a series, I'm not quite, because like I said, when things get basically a series is when the current, when the current has no place to branch off. So for instance, when I go through this resistor, right, all the current, when I go through, there's no junction. So we're going to see circuits, for instance, I'll draw you a quick circuit in parallel to see the difference. So those are two resistances. So now if you have the current going here, right, some of the current has to split off to go down this direction, and some of the current has to split off to go down in that direction. All right, if you remember, we had that junction rule that we'll have to start applying to multi-loop circuits when we get to those, which I think we'll get to. I think we'll introduce them a little bit, but I think we'll really go ho-hogging on them after the break, which makes sense. All right. So that's what we would see here. So in a sense, to be in series, it's defined as all the current goes through the same elements. All right. There's no branch, which you can see in parallel. There will be a branch. All right. Let's see what comes next. So potential difference across the real battery. All right. So I think what they're going to say is that I got it backwards, where we're going to call the potential difference. I did it both ways. So one time I got it right, one time I got it wrong. So we're calling this the EMF device, and then there will be some potential difference that's lower across the battery. you'll notice that they relate V is equal to the electromotive, the ideal EMF, minus this little IR. All right? And so and so let's see. Hold on. Is this important? Well, these stars are always important, but I feel like this star has to do with the last one. To find potential difference between any 2 points in the circuit, start at one point and traverse the circuit to the other point following any path, and add algebraically the changes in the potential. Yeah, that's from the last one. But the potential difference across the terminals, right, will be squiggle, the electromotive force, minus the internal resistance. All right? So you'll always see that our potential difference will be a little bit less than our ideal EMF value. Yeah, I got that mixed up in the beginning of the lecture. You can go back and watch it, but that's okay. It's still the same stuff. Now, when you ground a circuit, you're getting a circuit like this, and you will connect it to ground. So what this does, hold on. It's the symbol with the 3 lines that I just drew. So what this does is you're connecting it to something that is grounded, and you're ensuring that this voltage is physically actually 0. Right now it's been abstract and we can set it to anything we want. But if we ground the circuit, then that means that the negative terminal goes to ground, so we know that we have 0 potential at that point. And if we were to measure it, that's what we'd get. The power to an EMF device like this will be the current, right? Because the current will be the same, times the electromotive force. All right? And now, before we go on to multi-loop circuits, I want to check something out here. I want to see if this makes sense, because I really have a topic I'd rather talk about. I want to see if it's really important to do this. Oh, hold on. I think that'll take too long. All right. I want to talk about actually taking measurements, because there's just one part to it. So I'm actually going to skip ahead, and we're going to come back. So multi-unit circuits, the only thing I have to say about them is they give us these multiple loops. But for right now, we'll skip that until after spring break. And we have questions and examples to do that will take a long time. But what I want to talk about is how to make measurements. So I want you to notice, if you take out the meters here, so if we were to cross this out and to cross this out, we would actually have a single loop circuit. So I want to redraw the circuit. I don't know if I have space. In a way, and I want to show you the system, and this is what you're looking at here is the measurement. So we have a battery. With a little internal resistance. Make a box around this. So we'll call this R2, call this R1. Now I want you to notice this is a single loop system. Okay? We have here a single loop system. Now, in order to measure the current and the and the voltage you can create a loop with and just probe it. So basically, if you have this voltmeter here, you'd have two wires that you would just place on the system, okay? And then you can make your voltage measurement. It's really pretty easy. So if you can imagine, if these two pens, if the resistance is my head, and you have a voltmeter on the other end of these pens, I don't want to get ink on my head. You just put the probes in on the circuit and you measure it. These dots here, you kind of make it part of the circuit, but not really. And you'll understand why that happens when we learn about, you'll understand the reasons why this works, because when things are in parallel, the voltage in each branch will be the same. So you get the voltage here across the resistor, it'll give you the same voltage here. This makes measuring voltage really straightforward. To measure current, you actually have to take apart your circuit, right? You have to take apart something. You have to take apart something here, and you have to put in and rewire an amp circuit into your circuit. If you look at it, you can't probe a current here, because if you did, the current would have to leave the resistor and come out, right? And here, the current will just be part of the circuit. It'll flow through the meter, measure what it is, and then keep going around the circuit. Now, I think what I want to, the voltmeter and the ammeter are important, but there's two things. One, the best place to learn about these is in lab. Two, they're so fundamental that we really have to talk about them, even if we're just going to be using digital ones. But the other thing I want you to note, and I think in lab I would mention this all the time, and I would beat it, I almost want to beat it to a dead horse to it. But what you really need to understand is that this is the circuit being analyzed, all right? So if you were building this, you first build your circuit. Students make the mistake all the time of trying to measure everything. First you have a circuit, then you see how you can make it modifiable to current, right? Where could you break the circuit up? So you want to be able to break the circuit up, if it's just one loop, it doesn't matter, you can put it anywhere. But if you have branches, for every branch of the circuit you have, or for every loop you have, you'll need one place where you can put in that, you may need multiple places to put in the current, honestly. For each circuit element, you'll want a reliable place to put the current. But then you need to probe with your voltmeter, right? And you could probe either this resistor, or the battery, right? So keep that in mind. These are the analysis tools, the measurement tools, but you always want to build the circuit you are going to analyze first. Okay? And with that being said, we only have about 9 minutes, but that is not a ton of time to really start the next section. But that gets us through my discussion on AM meters. So that means when we come back, we can start with multi-loop circuits and end with RC circuits, hopefully. And yeah, that should do it. So let me take the attendance really quick, which I just do by taking a picture. So if you're expecting me to call your name, that's not going to happen. And this is good, though, because I actually have all the attendees. So hold on. Oh, boy. Let's see here. Picture. Okay. There we go. And I'll stick around in the room. If you have any questions, let me know. I am going to preheat my oven, though, very quickly, and then I'll be back. So we don't have lab lectures. Basically, I post a video, and you watch it and do it. It doesn't make sense for me for all of us to get together and only see it once and have a video of it when I can just make a video with the simulations and have it be a little easier with screen capturing, and then put it. You have to look in section B, Mustafa. That's where it is. Okay. Jesus, you can Skype me at 8 o'clock. Dinner is salmon and vegetables. So the next lab video I'm going to put up, remember the last lab video covers 2 weeks of lab, and technically we're on break tomorrow, so we won't we won't have a lab, but I will put something up probably by the end of the week for you to do. Okay. Yeah, I just look for it. I have to make one for Physics 1, so I'm probably going to make them tonight or tomorrow, and I'll just dump them up there. But the due date will be after spring break. Okay, no problem, Raphael. I'll take them as I get them, so I'll text whoever gets me first. You can stay here, like I said, till 8 o'clock. I'll be here, and then I'll sign out of the room. I'm going to stop recording now because we're kind of done, and I don't want the video to be extraneously long.